So on the last lecture, I started to talk about Wilkinson polynomial. So here it is from your book. So essentially, this is polynomial which of power 20, which has roots which are just natural numbers from 1 to 20. So 1, 2, 3, and so on till 20. So it's just x minus 1, x minus 2 multiplied on x minus 3, and so on till x minus 20. So if you will open all the brackets, so multiply all the brackets inside, so this is what you will get. So this is how it will look like. And it's interesting that if you will try to find, even using relatively sophisticated algorithms like from MATLAB, like F0, so Wilk poly, so it's essentially just this polynomial created as a MATLAB script or MATLAB function, if you like. So, and you even give exact root as an initial guess, as a starting guess. So what is interesting that the answer which you will get will be just these, right? So obviously you know that the exact root is 16 sharp, right? But here, already in the second digit after decimal point, you have an error. So the reason for that, of course, is in the following, that for example, the terms which you are adding, they are of very they can be very different in order of magnitude. As a result, when you will be adding and subtracting these numbers, right? So you will be losing precision because of the finite precision of the representation of the floating point numbers inside of your computer. So essentially, MATLAB uses by default double precision. So you would expect that you would get something like maybe not 16, but some significant number after decimal point, right? Of the right digits. But what you're getting inside, so that you're getting error right here. Okay. So what is interesting? Of course, if you will write your Wilkinson polynomial in this form, and you will substitute there 16, of course, you will get immediately the right answer, right? 16 sharp. Why? Because, of course, your algorithm will check whether this is the exact solution, and because you will have there x minus 16, so you will get exact solution. So it will give you exactly 0. So, and your algorithm will stop. So, but here, in order to get that, for example, 16 is an exact solution, so you need to substitute it, right? And subtract and add all these terms, and this is where you're losing your precision. Okay. So you see, Wilkinson said that for himself, it was the most traumatic experience during his career as numerical analyst. So that even very simple root, a very simple polynomial gives you that much trouble. Yes, also I just wanted to show you here the picture. So you remember we were considering previously these, which is nothing else, of course, but x minus 2/3 to the cube. So, and this is, you remember I was telling you that you are getting the wrong, even the wrong signs of the function when you were getting close to the exact root 2/3. So this is what happens so when you're performing computations. So because just, you see, it's 10 to the minus 16. It's of the order of the precision, accuracy of representation of the floating point numbers. As a result, so if it's plus 10 to the minus 16 or minus 10 to the minus 16, so your computer cannot distinguish that. So because of the finite accuracy of representation of the double precision numbers, or just any floating point numbers inside of your computer. As a result, your algorithm will start giving you troubles, because you remember, if you use, for example, bisection, which is usually robust, right? So, but if you're coming close to something like that, so bisection depends heavily on the sign of your function, right, to determine whether in this or another half of the interval you have your root, right? Because you remember, if your function is changing sign, right, and it's continuous there and has only one root, so then you know that there is your root, right? Because it means that if it changes sign, so 0 is somewhere there. Okay, so and here it start giving you troubles. Okay, I will stop sharing. Now let us talk about a little bit about the theory, how to figure out in advance that you can have troubles. So, okay, let us consider that let us consider our usual problem for root finding. F of x is equal to 0, and so let us suppose that R is a root. So what it means that if I substitute it here, it exactly gives me 0. Okay, now let us suppose that we are trying to find the root. Then, and we are just located somewhere x is equal to root plus just small delta r, small, with respect to r. So in other words, delta r on r way less than 1. Okay, so let us like that. So let us write what we will have. But also, so we substituted our x right here. So, and we would expect to have it equal to 0. So this is how would you think, right? So you're trying to find delta r. So you equation for delta r. But the problem is that really what you will have, because of this finite precision of the representation of the floating point numbers, you will get also some error contribution term. So essentially, this is perturbation of your equation. Due to finite precision. Okay, so, and as a result, if you will, so for example, what we had in the case of Wilkinson polynomial. So we started with our equation after we multiplied all the brackets with all these crazy terms, and then okay, so we just found some root. So, but this root is satisfying not the original equation, but instead it's satisfying this equation. So this equation, because inevitably when we perform floating point operations, so we introduce some error, right? Because of fine precision of representation. So instead of these, we satisfy these, and this is why we got not the exact answer, but the answer which was a little bit different, right? Okay, so let us try to figure out how to control or just predict what will be this inaccuracy of the root which we will find. So, so this is small value. Okay, so what we can do, we can perform Taylor expansion. So essentially this term would give me, we perform Taylor expansion around the root. Okay, and I will stop myself on the first derivative, so on the first correction. So and here we will have the same. And plus so-called O capital delta R squared. And this will be equal to 0. So this is that. So let me remind you what is O capital or big O notation. So it means that so big O delta R squared. So it means that if I take the limit when delta R goes to 0, O capital delta R squared divided by delta R squared, this will be some constant. So in other words, you can say that, in simple words, you can say that when delta R goes to 0, so your O capital delta R squared behaves like some constant delta R squared, something like that. So it's because we stopped on the first linear correction terms in our Taylor expansion, right? So this is why we got this. Okay, let us go further. So now, if I take delta R small enough, if delta R is small enough, then this thing is also small enough, right? Because it behaves, remember, it behaves like that. So let us just consider the case when we are close enough to the root so that this term is negligible. So because you see, these terms are proportional to delta R, right? So if delta R is small, so this term is proportional to delta R squared. So this term is vanishing faster than these terms, right? Okay, so it means that I can write the following approximate inequality. equality. Approximately equal to 0. Now, I need to remember that R is the root of my original equation of this one, right? So I will take this into account. So I know that this is equal to 0, right? As a result, we can let us group together terms with with delta R in the left-hand side and without delta R in the right-hand side. So this is what we will get. Okay, and from here I can factor out delta R, and then I will get the following: that delta R is approximately minus epsilon G of R divided by prime of R plus epsilon G prime of R. Okay, but if this is small enough, so for example, let's say this is a really small number, and this is usually what we have, because where this number comes from, it comes from the finite precision of representation of the floating point numbers. But in our case, we know that for double precision, so it more or less gives us, if we are talking about relative error, so it will be around 10 to the minus 16 or something close to that. So, so the result, I can neglect this term and I will get the following. So what you can see, this is a small number, and everything depends on this fraction, right? On this ratio. So we require here that f prime of R not equal to 0. Otherwise, we couldn't stop our expansion here with the first term, right? Okay, so this is so-called sensitivity formula for roots. So what we got? We got that if we have epsilon G as a perturbation of our equation, right? Then instead of the root, we will have a root plus some mismatch, right? Or some distortion of the root, delta R. And we found the estimation for this delta R. So in other words, we can write that it's so-called sensitivity formula for roots. So if R is a root of f of x and R plus delta R is a root of f of x plus epsilon g of x, so perturbed equation, then delta R is approximately minus epsilon g of R divided by f prime of R if epsilon is strictly less than f prime of r, so some relatively small number, and of course this already includes that f prime of r is not equal to 0. Otherwise, this formula is not defined, right? So let us do an example. So let us consider p of x, which is x minus 1, x minus 2, x minus 3, x minus 4, x minus 5, x minus 6. So it's just like some shortened Wilkinson polynomial. And then here we have a perturbation 10 to the minus 6 x to the 7th. So it means that this is my original f of x, right? And this is my, so epsilon g of x, right? So this is g of x, this is epsilon, right? Okay. So if we will try to compute the formula, the standard sensitivity formula, we will get the following, that delta r. So let us consider root r, which is equal to 6. So let us try to figure out what will be the distortion of this root if we will try to find the root of p of x if you will open all the brackets. So this essentially models what will be the error, like a distortion term, if we will open all the brackets, and we will have inevitably, due to fine precision of representation of floating point numbers, some some mismatch with respect to the exact values of the polynomial if we will open all these brackets, similarly to the Wilkinson polynomial. So then we will get, this is approximately minus, obviously, epsilon 6 to the power 7, right? Divided by, and here how to find what is the derivative, because essentially so it's just 5 factorial, so the derivative of f of x. So if you will have a look, so it's relatively easy to figure it out. Okay, now what it is. So you remember that this is really small number, right? But that is a large number, 6 to the 7th. So as a result, what we will get, it will be, okay, really plus or minus. Oh, okay, I will leave it epsilon here. 32.8 epsilon. So you see, this is 10 of the order of 10 to the power 3. So like 1,000 or 2,000, doesn't matter. And even if this is a relatively small value, 10 to the minus 6, right? So what this thing models, 10 to the minus 6, if you remember, is approximately the accuracy of representation, relative accuracy of representation, approximately, of course, of single precision numbers. So if you will try to solve this equation on a single precision computer, like most of microcontrollers, even if they have floating point units, so they are most of the small processors, even if they have floating point units, they work in single precision only. So, okay. So, if we will try to find the root r equal to 6, because of this distortion of our equation, so what we will get will be approximately 6.002328. So if you will try to find the root, so essentially this is a good estimation. So you see, we got the first several digits right. So if you will multiply this value by 10 to the minus 6, you will get exactly this distortion of the root. So which is 6 plus, okay, you can write it as 2, 3, 2, 6, 8, 10 to the minus 6, if you like. Because, pay attention, we have negative sign here, right? So we got positive sign here. So because epsilon is negative, so it will cancel with this sign. Okay, so as you can see, the first several digits of this distortion of the root, they are right. Okay. So this is so how we can introduce so-called error magnification factor. So error magnification factor, it's relative forward error divided by relative backward error. So essentially, where this comes from? Here, what is that? So essentially, what is, let me remind you what is forward error and backward error. So if we have a solver, so we have error of initial data here. So initial data. So, and here we have backward error. So in our case, the backward error, so what was the error in the initial data? It was this distortion of our equation, right? So, and then we were getting the solution. Obviously with some error, and this was so-called forward error. So essentially, if we got r plus delta r, so this is the forward error, while in backward error, so if we had f of x plus epsilon g of x, so this was the backward error. So essentially, this was the error on input, right? And this is the error on output. So idea is how they are related. So we are trying to figure out the magnification factor, error magnification factor. So and by definition, we introduce it as a relative forward error divided by relative backward error. Why? Because if you will multiply this fraction on the backward error on the error which we had at the input data, right? So it will give us the error which we will get on the output. So how the error of the input data will be magnified on the output. So essentially, if you will use this this fraction, so you will get that so what is the relative forward error is delta R divided by R, right? So the relative error of the root. And relative backward error is essentially epsilon G of R divided by, you can write it as F of R plus epsilon divided by G of R. By G of R. But what it will give us? So it will give us that, so this fraction, so using the formula which we just derived, this one, so we will get that it will be nothing else but minus epsilon G of R divided by R F prime of R divided by epsilon. So this is nothing else but magnitude of G of R so here it is. So essentially, this is error magnification factor. If this error magnification factor is large, then it means that, so we usually say that in such a case, the problem is ill-posed. So because the small error of the input data will result, and it's inevitably there because of fine precision of representation of the floating point numbers, or for example, just because if this data was measured, was some measuring, so we always do measurings with some finite accuracy, right? But then if the error magnification factor is large, it means that this small error on input can be magnified by a huge number. So, for example, let us try to figure out the what is the error magnification factor for the Wilkinson polynomial around root R equal to 16. So, okay, let us try to investigate influence of term x to the 15th, error in the term x to the power 15th on root 16 of Wilkinson's polynomial. Okay, so essentially we can say that Wilkinson, perturbed Wilkinson polynomial will be the unperturbed one plus some epsilon g of x, where g of x is, as we know, so you can have a look at the book and you will see that it's nothing else. I mean, it's just the term with the power 15. So it's 1, 6, 7, 2, 280, 280, 820, x to the power 15. So this is the term, right? But of course, okay, so where the epsilon comes from, because this theme, so when we will be performing computation, so really you can say that it's perturbed due to finite precision. So, okay. Now, if you will use, if you will try to evaluate through sensitivity formula for roots delta R, so it will be approximately 16 to the 15th power, the root, multiplied on 1, 6, 7, 2, 280, 820, and on epsilon, divided by 15 factorial, 4 factorial. So which is approximately 6, 14, 32 by 10 to the 13th epsilon. Okay, so as a result, so what we can say that, let us say that epsilon is nothing else but machine precision, right? Which is approximately 222, 10 to the minus 16th for the double precision numbers. So the result, delta R, will be approximately, so I just substituted here, so it will be approximately plus minus 0.036. So it's more or less what we observed before. So because R plus delta R would be approximately 16.0136 instead of just 16 exactly. So let us try to figure out their magnification factor. So it will be G of R magnitude divided by R, F prime of R. So which is nothing else. If you will substitute here G of R and the value of that, so which we evaluated here, so you will get nothing else but approximately 3.8, 10, 12. So it's a huge number. It's huge. So essentially, you are losing 12 digits out of 16 correct digits for the double representation of numbers. So you lost. So you see, these two digits are right. These digit is right, and these digits are already wrong, right? So essentially, you're losing most of your digits. So if error magnification factor is large, then problem is ill conditioned. If it is small, this is small, or usually it's something like not that far from 1, let's say. So this is what means small. Then the problem is well conditioned. So you see how to understand whether you have some serious troubles or not. So for example, you know that the error of your measuring, right, measurements, which provides you input data, like initial data for your problem, is, let's say, 10 to the minus 3. And if magnification factor is something like 10 to the power 6, you know that you're losing practically everything. So as a result, your error will be, relative error will be just huge. So it will be way more than the error of the initial data. So essentially what you will be getting will be complete garbage. From the other point of view, if your error magnification factor, let's say 10, you know that, okay, my relative error on input is 10 to the minus 3. So I'm losing 1 order of magnitude. So my error will be of the order, on the output will be of the order 10 to the minus 2, right? So what you can say as a result, if this accuracy is enough for you, so then you could say that, okay, I'm okay with that, so I can live with that. So, but the thing is that you need to figure out to evaluate this error magnification factor, and if this error magnification factor is huge, like here, for example, then most probably, so you know approximately how many digits you can believe in. So in many cases, what you do, so you're, for example, what you can try to do, you can check, you can try to figure out this error magnification factor, trying to use introducing different errors on the input on some model simple case, and then figuring out what is going on with your system. So this is, by the way, one of the problems with the meteorological predictions, because for meteorological predictions, for example, you have just the most powerful supercomputer available in the world, or maybe even 10 times more powerful. But anyway, for the so your initial data, which is, for example, temperature of the air and wind speed, right, in every point is not known. So you cannot create the infinitely fine grid on your Earth's surface, right? What you can do, you can just, and this is what is usually done. So, for example, here in Albuquerque, one of the weather stations is in the airport. So you have some relatively sparse grid of weather stations, which will provide you with realistic data. Of course, they also have finite precision, but you can neglect that. So so that the precision is finite in those points. You can say that, okay, let us consider it almost exact. But the problem is that, for example, in order to determine the weather in East Mountains, so on the other side of Sandia Mountains, what you need to do, you need to figure out approximately, using some model or the methods which we will study later. So you will use some data from other weather stations, but there are only few of them, and then use this data in order to extrapolate this data on some on more spatial points. As a result, your input contains errors intrinsically, because this is just a model. It's not perfect, of course, and it will never be perfect. And if you will study at some moment ODEs, you will figure out that the description of atmosphere. So one of the simplest models for atmosphere description is so-called Lorentz model, which contains 3 nonlinear equations. And these models exhibits some behavior which is called strange attractor. So essentially, even if you start with a really small difference of your initial data from the 2 points which differ just a little bit, after some time, the trajectories of your solutions, or you can say the predictions, will go apart, and they will go apart pretty fast. So as a result, it just comes from mathematics. So just from the nature of these equations, and it looks like it's inevitable. So it means that it doesn't matter how powerful is your supercomputer which you use for weather prediction. So what happens that because your initial data is using any realistical measurements, so contains an error. So it doesn't matter how powerful is your supercomputer. Because of pretty big error magnification factor, you cannot predict weather exactly with good accuracy for more than a few days. So as a result, this is it. So as you probably observed many times, okay, for 2-3 days, the accuracy of prediction is relatively okay, and then everything what is further, so essentially you can toss a coin and will get approximately the same idea whether you will have a rain or not after 4 or 5 days. So this is because error magnification factor of this problem is huge. So as a result, the initial errors, or you can say large enough. So initial errors of your in your data, so they are getting magnified, and after a few days, so you're getting the longer is the time for which you want to forecast your weather, so the higher is this magnification factor. And after some time, so of course errors in the initial data will just essentially ruin everything. Okay, so this is extremely important theme, error magnification factor. So and I want you to understand this. So we considered very simple examples, these polynomials, but just they give you good illustration of what can happen if just the problem has this huge error magnification factor. Then even the very small errors on the input, they give you serious troubles on the output because error magnification factor is huge. Okay, now we studied before the Newton's method, and I introduced what is, so let me remind you. So, excuse me, xn plus 1. So it's not his initial guess. So if I will ask you, for example, during the test to write Newton's method, Newton's algorithm for some specific function, what you need to do, you need just to substitute your function and its derivative here and write it as xn plus 1 equals to some function of xn. So you start from initial guess and you produce successive iterations. It's Newton's method. Okay, so I told you before that the Newton's method has so-called quadratic convergence. So definition, I believe I gave it before even, but let me give it again. Epsilon n, the error after step n of an iterative method. The iteration are quadratically convergent if and this is some constant, finite constant. Or in other words, you can say that is approximately, pay attention that because this works only when n is pretty large or large enough, let's say. So your behavior is approximately like that. So linear convergence, you remember which we had. So and I have proven that, for example, for bisection. So we had so you see it's in the first power, so linear function, right? So and for fixed point iterations, so we had these. So and you remember that for convergence, sufficient condition for convergence was this is less than 1, right? So the error is decreasing. So okay, now let me prove that Newton's method has quadratic convergence. Okay, and even more, so I will formulate it as a theorem, so that if f is twice continuously differentiable, it means that two derivatives exist and they are continuous. So, and f of r is equal to 0 and f prime r is not equal to 0, then method Newton's method is locally and quadratically convergent and quadratically convergent to R, and even more, limit when n goes to infinity, epsilon n plus 1 divided by epsilon n squared. So our m is f prime prime r divided by just this. Okay, proof. So quadratic convergence usually is way faster, way faster than the linear convergence. So This is why, for example, in many cases, what you could do, but of course, the problem is with robustness of this convergence. So if you cannot guarantee these conditions, so then essentially what you do, you can start, for example, using bisection, which is very robust method, right? And then the final polishing of the root you can perform with Newton's method. It will be just faster and more efficient. Okay, so let us write Newton's method we can rewrite as fixed point iterations. Iterations in the following way, that g of x is x minus f of x divided by f prime of x. Because pay attention, here is the formula, right? So if you would have something like that, g of x, right? X equal to g of x. So then you know that fixed points would be nothing else but these, right? But because your formula is exactly this, so you could say that this is nothing else but fixed point iterations for this particular problem where g of x is equal to that. I also mentioned about this on the previous lectures. So, but okay, let us compute the derivative. So you remember the sufficient convergence condition for fixed point iterations, that the derivative has to be, magnitude of the derivative at the root has to be less than 1. Okay, so if I will try to find the derivative of that, this will be 1. And here is derivative of the fraction. So, or if you will, if this is not equal to 0, so which we required, right? If you open all the brackets, so you will get f of x, f prime prime of x divided by f prime x. From the other point of view, so at the root, this is 0, right? So at the root, because at the root, this goes to 0. So f of r equals to 0, right? So then it means that this is locally convergent because it's less than 1, right? Obviously. Okay, so let us prove quadratic convergence. Then what we will need to use, we will use Taylor's formula. So f r is, so let's say that fn, we have xn, and so approximation of the root r at nth step. Just to remind you. So and then it will be fxn plus r minus xn f prime at xn plus f prime prime at some cn, just a remainder term. To factorial, which is equal to 2, right? Okay, and cn belongs just to the interval between xn and r. Okay, because r is the root, so this has to be equal to 0, right? Because r is the root, and we are getting that this is 0 f of xn plus f prime at xn r minus xn plus r minus xn squared divided by 2 f prime at cn. So we can write it in the following way. So I just divide by f prime, just divide all that by f prime at xn, and then I will get and bring this term divided by that to the left hand side, and this is what I will get. Xn divided by f prime at xn, it's equal to r minus xn plus r minus xn squared divided by 2 f prime cn divided by f prime. Assuming, of course, that this is not equal to 0. So after some rearranging, this is what we can get, that x. So I will just bring these to the left hand side. So, and I will get that xn minus f of xn divided by f prime of xn minus r. This is nothing else but xn plus 1 for the Newton's method, right? And this is nothing else but here we have r minus xn squared divided by 2 f prime of cn divided by f prime. So what is that? So how can I write it? I can write it as this. Let me remind you that this magnitude of that is exactly the error on nth step, and this, which is xn minus xn plus 1 minus r. So if I take the absolute value, so it will be error on n plus 1 step. As a result, I'm getting that error on n plus 1 step is error on nth step f prime cn divided by 2 f prime xn. So, but when we take the limit, so we have proven that the xn, when n goes to infinity, will converge to r, right? So it means that the interval between xn and r will be getting smaller and smaller. And in the limit, if I take the limit when n goes to infinity, so I will get nothing else but this. So exactly like in definition of quadratic convergence. So this is what we have. But now there is, if we consider, let me consider the following. So I have proven the theorem. So now let us consider the following problem. F of x equals to x squared. So obviously the previous theorem is not applicable here. Could you tell me why? So which condition for the theorem is violated?
F prime of r is equal to 0 in this case.
Yes, because obvious root here, right, is r equal to 0. So r is 0, right? But if you will try to find the derivative, so this is 2x, so the derivative, so f prime at r is equal to 0, right? So obviously what will happen that this condition is violated, right? So it means that the previous theorem about quadratic convergence is not applicable here. Okay, let us try to figure out what will happen with our, just let us write formally the Newton's method. So let me remind you. The formula which we derived before is this one. So it will be xn minus xn squared divided by 2xn. So this is, you can write it as 2xn squared minus xn squared divided by 2xn. Okay. And this will give you nothing else but 1/2 xn. So what we see that if we will start from some point far from the root, so what will be happening on every step, our distance from the root, which is xn, right, because root is 0, will be, how we can write it, xn plus 1 minus 0 equals to 1/2 xn minus 0, right? So this is error on n plus 1 step, error on n step, right? So the error will be decreasing by 2. So instead of quadratic convergence, we again obtained linear convergence, right? So by the way, so once again, this is what I want to get from you when I ask you, please write down the algorithm for Newton's method for this particular function, right? I gave you a function. This is the formula for the Newton's method, right? So what you need to do, you need to substitute instead of f and f prime corresponding function which you have. So, and this is the final answer which I would like to get from you. So this is, I mean, one of the standard problems on the tests. Okay, so this is what we have got. So you see, when we violate the condition of applicability of the previous theorem, so what happens that Newton's method can still converge, right? But what happens that we are getting completely different result. We are getting linear convergence, right? Okay, now let me consider another example. So f of x is x to the power m, where m, just x to the power m, doesn't matter. Okay, so then Newton's method again, xn minus f of xn divided by f prime of xn. So could you tell me what will be, what I will have here for this ratio? Could you please just tell me? What is this?
That's just x to the n.
Xn to the mth power, right?
Mm-hmm.
And in the denominator?
It'll be m times x to the n to the m minus 1.
Exactly. So thank you. So as a result, if you will have a look here, so what I can bring these terms to the common denominator, and this is what I will get. So it will be m minus 1 divided by m xn, right? So I got that, okay, once again, here x equal to 0 is the root, right? Obviously. So I got this equals to or I can write that, sorry, n plus 1. Yes, I can write that this I have linear convergence for and with this coefficient. So okay, now could you please tell me for this particular root, what will be more efficient, Newton's method or bisection method? They both have linear convergence, right? Okay.
Would bisection be more efficient only in the case when m is equal to or less than 1? Or
Okay, so in this particular, yes, you're almost right. So in this particular case, right? So we have, so for bisection method, if you remember, so we have this, right? So really, in this case, in the case of x squared, f of x equals to x squared, they have the same rate of convergence, right? Because every time on every step, your error is decreasing approximately by 1/2, right? Clear or not? Now, if m is equal to is more than 2, what we will have? We will have here, let's say 2 plus whatever. Let me just, for simplicity, consider m equal to 3. So then I'm getting 3 minus 1 divided by 3 epsilon n, so which is 2/3 epsilon n. 2/3 is strictly more than 1/2, right? So it means that my error will be decreasing slower. Is it clear or not? So for m equal to 3, what will be more efficient, bisection or Newton's method?
Bisection.
Of course, bisection, because on every step for bisection, error is decreasing by the factor of 2, right? Or you can say by the factor of 1/2, while here it's decreasing by the factor of 2/3, right? So which is not as fast. Okay. Now, okay, I can formulate the following. So I will not prove it, but I can formulate the following theorem. You can do exactly the same analysis like here. And so if you have the root of the order m, so you remember I told you that if you have a root of the order m, so you can represent it as x minus r to the power m g of x, which is not equal to 0 at x equal to r, right? So this is how it will look like. So and then you can say that if you come close enough to the root, so you can say that this is kind of a constant, right? Which is just value of this function g of x at x equal to r, and then so you have just this, and if you will shift your coordinate system to have origin at the root, so you will get exactly this expression. So as a result, I can formulate the following theorem that assume f of x on the interval is m plus 1 times continuously differentiable. Which means derivative exists and it's continuous. So, and f of x has a root of multiplicity m at r, or x equal to r. Then Newton's method is locally convergent. What does it mean locally? If you start close enough to the root, right? Because we know that this the theorem which we used, this Banach theorem, or if you like, I mean this the theorem for convergence of fixed point iterations, right? So it's only local statement. So it means that you need to start close enough to the root. Okay, so is locally convergent to R, and the error epsilon n at n step satisfies n goes to infinity, epsilon n plus 1 divided by epsilon n, which is minus 1